So far, we've talked about heat calculations when it has to do with physical changes. So that means, things like boiling, freezing, vaporizing, condensing, all of that stuff. We have not really talked about chemical changes yet. So this lesson is all about calculating heat when it's in chemical reactions. So it's called thermochemistry, right? The heat, thermo, involved in chemical reactions. There are 4 indicators of a chemical change, and pretty much all chemical reactions are going to involve a change in energy. It's either absorbed or released, and a lot of times that's heat energy. So think about thermochemistry. Reactions can be labeled as either exothermic or endothermic. We've talked about these prefixes before. Exothermic means that it's releasing heat energy. So that means the reactants do contain more heat than the products do, so that change in heat is released. So that change in heat of that substance would be a negative value since the products have less heat than the reactants. You end up with a negative change in heat. Those things are going to feel hot. If you put your hand on that beaker, that heat's going to be going into your hand. So these guys feel hot. The reactants have more potential energy than the products, so that extra energy is released into the surroundings. So heat, if you look at a chemical reaction, if you see heat listed on the product side, that tells you that this is an exothermic reaction. That heat is being released out with the products. So endothermic reactions are the exact opposite. So an endothermic reaction is absorbing heat energy. So which means the reactants have less heat than the products, so the heat gain is going to be positive, right? It's picking up heat energy, and it's going to absorb it from the surroundings, so it's going to feel cold. If you put your hand against a beaker that's absorbing heat energy, it's going to be pulling heat from your hand. It feels cold. So in order for these reactions to happen, they have to absorb heat energy. So therefore, you're going to see heat written as a reactant. So if you look at a chemical reaction and you've got some kind of kilojoules of heat energy, and it's on the left-hand side reactant, that means that that heat has to be absorbed in order for that reaction to happen. That tells you that's endothermic. It has to absorb that energy. So these diagrams are potential energy diagrams, and it shows the energy either being gained or lost. So you can see that this top one, the reactants have more heat energy than the products, so it's exothermic, that amount of heat, whatever it is being released out into the environment. Endothermic is the opposite. Reactants have less heat than the products, so that amount of heat has to be gained by that substance in order for that reaction to happen. So the amount of energy involved in chemical reactions can be calculated if you're given the heat of formation of both the reactants and the products. So the heat of formation, and that's another HF here, is defined as the heat that is either absorbed or released during the formation of 1 mole of that substance from its elements. So literally, if it's for carbon dioxide, it's how much energy is absorbed or released when 1 carbon and 2 oxygens come together to form that molecule. You're going to be given a lot of those constants. They're going to be given to you in a table. It's just a matter of pulling the right one for the right substance. And so the equation, the change in heat of the whole reaction, is going to be the change in it, right? So it's going to be the total amount of heat in the products minus the total amount of heat from the reactants. So you're going to have to add up heat of products, add up heat of reactants, and then subtract them. Now, if you notice in this table, you're not given the heat of formation for elements, because elements don't take energy to form. They are elements. So elements, the heat of formation is 0. So it's not going to be given to you. Don't freak out. That's because it's 0. You don't have to worry about them. So let's look at our first one. Calculate the heat of formation for the following reaction. We have to determine whether it's endothermic or exothermic. We're missing our little arrow here. There's our arrow. Okay, so which remember the total change in heat is going to be our products minus our reactants. It's our final minus our initial. In a chemical reaction, products are our final, reactants are our initial. So let's take our sum of our products. So I'm going to use a bracket here to represent the sum of our products. So we're going to have 4 NO. So if I have 4 moles of NO, now we need to look up the heat of formation of NO. So go to the table up at the top. We're looking for NO. Found it. So we've got 4 moles times 90.2 kilojoules per mole, plus, now we have 6 water, so I have 6 moles of water, just using those coefficients there, times water. Now I can see that water is a gas, so when I go up to this table, I've got to pull water as a gas. Now, heads up, that's a negative value. I have negative 241.8 kilojoules per mole. So parenthesis, close my bracket. That is my products. Now I need to take that guy and I need to subtract. I'm going to do the same thing, but with my reactants this time. So I'm going to open my bracket. I've got 4 NH3, so I'm going to have 4 moles of NH3 times, and I'm going to look up NH3 on my table up above. There is my ammonia. Again, it's a negative number, watch out. Negative 46.1 kilojoules per mole plus 5 oxygens, so then I would say 5 moles of O2. Now we've got to look up that heat of formation, and it's not on here. Remember, oxygen is just an element, and elements are 0. Close that bracket. So now, doing the math, heads up, there's a lot of little multiplication times negatives and then adding negatives. I suggest that you write out the sum of the products, write out the sum of the reactants, and then subtract them separately, but everyone works out differently. So I'm going to do my products first. 4 times 90.2 plus 6 times negative 241.8. I'm going to write that sum. That sum is, let's see, negative 1,090. And if you look at your units, we've got moles and we've got kilojoules per mole. So the moles are going to cancel out, and my answer units are just going to be kilojoules. So kilo means 1,000. So here's just 1,000, every kilojoule is 1,000 joules. Now I'm going to do the same thing for my reactants. I'm just going to multiply them and then add them together. So 4 times negative 46.1, 5 times 0, I don't have to worry about that. So then I'm going to subtract negative 184.4 kilojoules. Close my parenthesis there. That's my parentheses. So now it's just a matter of doing a simple calculation. So negative 1,090 minus negative 184.4, you're going to get as your answer negative 905.6 kilojoules. There we go. And we have a negative change in heat. So is this reaction endothermic or exothermic? Well, it's negative, so that tells me that this is an exothermic reaction. What's really neat about this is if I know it's exothermic, maybe we want to go ahead and go in to our chemical equation and add that amount of heat energy. So I can actually go in here and write it as a product since it's exothermic and say that, cool, if this reaction happens, I'm going to get 4 NOs as a gas, 6 moles of water as a gas, but I'm also going to get 905.6 kilojoules of heat energy. So I can actually go into that ratio, 4 moles to 6 moles to 905.6 kilojoules. And I chose to put it on the product side since it's exothermic. By placing the amount of heat energy lost or gained in a reaction, we can treat it as any other part of our stoichiometric calculations, which is a scary word for our mole ratio. So in example number 2, I can see that the kilojoules have already been placed in the equation. So right away we can say, well, is this exothermic or endothermic? This is exothermic. It is releasing heat energy. So now that we know that this is exothermic, we can now just do this as a mole calculation. So we're going to start with our given, see how many grams of ethane must be combusted to produce 1,250 kilojoules. So we're going to start with 1,250 kilojoules of energy. And that means same process, we're going to cancel out our kilojoules and we can get it to moles. This is our mole ratio. I know that I have 345 kilojoules of energy, and we're trying to find grams of ethane for every 2 moles of ethane. Now that we're to moles, it's just a matter of getting it to grams. So just our regular mole calculations, we need to find the molar mass of C2H6. So the molar mass of C2H6 is 28.06 grams. So we have successfully canceled out our kilojoules, canceled out the moles, and we've gotten to grams. So now we just need to multiply across the top and the bottom and then divide. And when you do that, you're going to get 203.3 grams of C2H6. Now we can go ahead and round that to 3 sig figs since our number we're starting with has 3 sig figs of 203 grams. So our third example, we're asked to find the energy change involved in the combustion of ethylene if we have 56.3 liters of carbon dioxide. So I know this is going to be a conversion because we're starting with liters and we're asked to find the energy change. If we're going to have to do a conversion, I am going to need a balanced chemical equation for this. So let's think about this. We've got combustion of ethylene, so I know I have a C2H4, and if it's combustion reaction, I know I have oxygen. And I know the two products are going to be carbon dioxide and water. So now we can balance this guy. So the first thing I would do is I'd put a 2 in front of a carbon dioxide to balance my carbons. I would put a 2 in front of water to get 4 hydrogens. And my oxygens, that's going to give me 4, 6. So that means I'm going to need a 3 in front of my O2 to get 6 oxygens. Now I have a balanced equation. Let's write our givens underneath it. So I've got 56.3 liters carbon dioxide, and we're asked to find energy. So here's the problem. We don't know the energy. Now, I made the assumption that this was a combustion reaction and it's going to be exothermic, so I did put my question mark kilojoules at the end. But we're going to have to find the heat of formation to find out how much needs to go in the equation. So we're actually going to have to do 2 different things here. First thing we're going to have to do is find the change in heat. Remember, that's your products minus your reactants. And then we can do the stoichiometry to calculate that. So, first thing we're going to do is we have to find the total heat of our products. So our 2 products are going to be 2 moles of CO2. So we've got to look up our heat of formation of CO2. Is negative 393.5 plus 2 times 2 moles of water So now water here, we're going to have to make that assumption. Since the combustion reaction is going to generate a lot of heat, I'm going to make the assumption that the water is a gas on a test or whatever that would be given to you. So I've got negative 241.8 of water. Close that bracket out. There's our products. Subtract out our reactants. So reactants is going to be 1 mole of C2H4. Let's look up. That's heat of formation, C2H4. There it is. 52.3. And don't forget, oxygen is 0. So now let's calculate this. 393.5 times 2. Plus 2 times negative 241.8. So our products here are going to be negative 1,270.6 kilojoules. I'm going to subtract our, just 1 mole of 52.3 kilojoules is going to give us negative 1,270.6 minus 52.3. So our change in heat here is going to be negative 1,322.9 kilojoules. So now I can go up, put that in my equation, 1,322.9. Now we can do our stoichiometry. So we're going to start with our given, 56.3 liters of CO2. Cancel out our liters, get it to moles. 22.4 liters. Now I can say that every 2 moles of CO2 is going to create 1,322.9 kilojoules of energy. Multiply that guy out, 56.3 times 1322.9 divided by 22.4. Gotta multiply that by 2. we're going to get 1,662.5 kilojoules. Now, since this is releasing that amount of heat energy, let's go ahead and make that sign negative, showing it's being released.